Hello, so today we are going to do this problem, which is part of Leetcode Daily Challenge, search insert position. So what this problem says is we get a sorted array of distinct integers and we get a target value. And what we want to do is return the index if the target value is found, so the index of target if we find it in the array. If we don't find it, we want to return the index of where it would be if it were inserted in order, right? So either we find it, so we return the index for it, or we don't find it and we return the index that it would be in if we had inserted it and maintained the array into a sorted order. Okay, and the problem says that we must write it in O of log n time, because O of n is easy, right? You just go and check each element, but here we want to do it in O of log n time. Okay, so how can we solve it? Well, we can use binary search because that's exactly what binary search does. Binary search has time complexity of log of n, but with binary search we have a condition where we need to find a monotonic function, right? A monotonic function basically means that a function that over the numbers you are doing it on, it starts out as either false, the function itself, so this would be f of x, and this would be the number's value, so x. But once the function becomes true, it stays true. That's what monotonic means. Some variants may be that it's true and then it becomes false, it stays false once it becomes false. But most common use case is using this here, right? I will attach in the description a video I did in-depth explanation of this method of thinking about binary search. So you can take a look if you are not familiar with it, but this is roughly the gist of it. And then once you find this function, you can just choose a low and a high value where you maintain an invariant that low always needs to be false. So one edge is always low for low and the other edge is for high. So one edge is always false and the other edge is always high, is always true. Okay, and for the boundaries for low and high, you can choose just something outside of your search boundaries so that you don't, there is no risk of an error, right? And with this method you will never get, I've been using it for a couple of years now, and I never get an out of an out of one error, or like an infinite loop because I basically misassigned mid or misassigned high or low. If you follow this method, your binary search should be error proof. So how do we do it? So here for our function we are looking for a value target, and if we don't find it we are looking for its insert position, right? So how do we do that? Well, what we are looking for, the monotonic function that we can use here is actually just that the value in the array at x is bigger or equal to target, right? Why is that? Because if you do it this way, then first it's not bigger or equal, it's smaller, like with smaller values. So for example with 1, 3, 5, 6, and with target is equal to 5, then first with 1 it's smaller, so this function here is false. So if we take this as our function, then with this we get here false. With 3 is smaller than 5, so it's not bigger or equal to target, so false here. But here it's bigger or equal, it's equal, so we're true. And here it's bigger, so true. So you can see, and because the array is sorted, as you get more values, it's always going to be true because it's bigger or equal to this one. Then for something bigger, it's going to be still bigger, right? So that's the idea. So now we know our monotonic function, and so now we can just assign a default value for low and high. So for low, we want something outside of the boundaries so that we don't have any problem. So outside of the boundaries, let's just use -1 because we start here at 0. And this is the length, and -1 is the length of the array. So outside of the boundaries, we can just start off with n, right? That way we are guaranteed that we didn't pick up a problematic index, because what if the value is 5 still, but what if the array is 1, 2, 3, right? Okay, so that's why we pick n, so that we maintain that high is always true, because if we pick a high to be here, then this is false for this use case, so we don't have the invariant that high is always true, right? So that's the idea. Now another use case where to prove that we need low for high, low to be -1 is what if we have something like 5, 6, 7, and target is equal to 4, right? So if we choose low here, then this is actually not smaller than target. The f of x is not false, right? It's true. And so we pick -1 so that we don't need to worry about that, okay? So with this method here, it will work in all use cases, okay? Okay, so now we know our function that we'll check. We know low and high, so how do we move the mid, right? And when do we stop our while loop in binary search? Well, we want to maintain that always low and high are false. Low is the function for low is false, and function for high is true. So we can stop when we are here. When low is here and high is here, we should stop, because why? Because we are looking for the first true value. That's what we are looking for. First true value, because that means it's either the target itself, right? Or it's the place we will need to insert at. So for example, here, in this case, when t equal to 5, we will stop at when low is at here. So we'll stop when low is here, and high is here, right? And this is our answer, right? But let's say we had an array like 1, 3, 7, 8, right? And t is still equal to 5. Then we will stop when low is here still and high is here, but we will return this, but this is the right position we should return, because this is the right insert position. So it works whether target is there or not, okay? And so here, what does this mean? This means that we will stop when the difference between high and low is just 1, because that means we found the first true. Okay, so our while loop for our binary search is going to be while high minus low is bigger than 1. And then we can just have our mid value, which is going to be just low plus high divided by 2. So we'll do it with binary like this. And then we will, after that, we'll just check if our function here is true, which is basically that the num at mid is bigger than or equal to target. Then what do we want to do? In that case, that means basically we are in a case where our function is true. So what that means is mid is either here, or maybe it's something like this here. So either it's the first true or somewhere down the line. In both cases, we want to maintain that f of high is true, the invariant, but we also want to reduce our window of search for high to be at mid, right? So we can do mid -1 because maybe our mid is here, and if we do mid -1, then we will get a false, right? But there is no need to check after mid, because we know already that mid is true, right? And so here, this means that we need to say that high is equal to mid. Okay. Now what about if it's smaller, right? If it's smaller, that means our function returned false, right? So again, we still want to maintain that f of low is false, this invariant here. So let's say our mid was here, then we want to just set low here, because we don't know, maybe the mid was here. If we set it to mid +1, then maybe we'll assign to low a true value, and that violates our invariant, right? And so we want to just say, reduce our window, but keep low invariant to be false, right? And so here we will say low is equal to mid, okay? And when we are done, we exit the loop. What do we need to return? Well, the first true is actually what we need to return, right? Because that would be the index at high. And so here we can just return the index for high. Okay? And that's pretty much it the way we'll do binary search using this method here. I hope that was clear, and the time complexity is going to be of ligand time. We are not using any extra variables, any extra arrays or something, so it's of one space. Okay, so let's write this function and make sure it passes test cases. Okay, so this is the solution that we need to do. So as we said, saw in the overview, we need low to be -1 and high to be n, and then we stop when the difference is just 1. So when the low is in the last false and high is on the first true, and then we calculate the mid, and we check if this basically means that f of mid is true. So this is f of x is true, and so we push high to be at the mid position, otherwise that means it's false, so we push low to be at the mid position, and at the end we just return high because that's the true one. That's the one where f of x is true, which means basically the number is bigger or equal to target, so that's what we're looking for. And so let's just run this here and make sure it passes. Cool, and that works. Yeah, that works properly. I'll attach the video that explains this binary search method in more detail. You can take a look. And yeah, that's pretty much it for today's problem. Please like and subscribe, and see you on the next one. Bye.